All right, in this example 2, we're going to take a look at what happens when the surface area is not at a constant depth, but it's oriented in such a way that the depth or the pressure acting on the surface changes as we consider different points on that surface. So this would be the case of the side of the box that was described in example 1. So here I just copied that same diagram that we had in the previous example or the previous video. In the previous video and in example 1, we calculated the fluid force acting both on the top and bottom surfaces of this box. But for the top and the bottom, the pressure is constant because the depth is constant on those two surfaces. But in this example, we're going to take a look at what happens when we are looking at the side of the box where the depth changes continuously as you move from top to bottom. So in this case, what I'm going to do is instead of looking at this picture and this diagram in 3D, we really don't need all this information. So really what I'm going to do is just take a look at a slice of this. I am essentially just interested in where the water level is relative to this side of the box. So imagine that we are going to look directly onward from the right here at the side of the box from very far away. If we were to do that, then what we would see is we would see that we've got the water line. So I'll go ahead and say this is the surface of the water. Or whatever fluid. It is water in this case, though. And then we would have just our box, or the side of our box. So 2 meters by 5 meters. And we know that this distance here is 3 meters. So I'll go ahead and just do a little measurement here to say that this is 3 meters. Okay. So we don't need the whole 3D picture. This is much easier for us. That's what we need to know. So let's erase all of this stuff since that's not really needed. Okay, now that we have the essentials, we can get started on figuring this out. So there is a very general procedure listed here in remark number 2. And this is essentially how every fluid force problem will go. You are going to determine the fluid pressure at some arbitrary depth y. So what I'm going to do is I am going to just consider a little slice. And I'm going to go ahead and say that I made this slice at some y value y. So what I'm going to do is say that the surface of the water coincides with y equals 0. So that's 0. And then I am going to direct my y-axis, the positive y-axis, downward. You don't have to do it this way. It just eliminates the need to have this negative. It really doesn't matter as long as you are being consistent. Some people don't like that, so it's up to you. Okay. So in this case, if this is the y equals 0, then this distance 2, right, all the way down to this arbitrary slice, this is just at some arbitrary y value y. And of course, whenever something is tethered to the x-axis, which that's what this line is, y equals 0 is the x-axis, we're allowed to call that distance y. So in this case, the depth is actually given by y. So we know the depth. So the depth is y. 2, we need to know the area of a little thin strip. So some people like to actually draw a perceptible rectangle and shade it so they can see the rectangle. And we want to find the area of this rectangle. Now, the basic idea in any Calc 2 problem where some quantity varies continuously, and you want to figure out what that quantity is, you would need an integral to add up all of those little quantities and how they vary continuously. Well, the basic idea is we want to know what fluid force is. Fluid force will vary continuously if the depth varies continuously over your surface, and in this case, that does happen. So, what is fluid force? Well, fluid force is the fluid pressure times the area upon which that pressure is acting. So, if we take our rectangle and split it up into lots of little thin horizontal strips, so strip 1, strip 2, strip 3, strip 4, strip 5, so on and so forth. And if each of these little thin horizontal strips is really small, so this width here, the height, I guess you could call it, is just some little change in y. So we're going to consider this to be, or to have a thickness of dy. So oftentimes when I do these problems, I don't actually draw the rectangle itself. I just draw a horizontal line because whenever you draw something in real life, that stroke actually isn't a true line because it has a thickness. It's really a rectangle. So I just say dy, and then I need to figure out what this width is. So whether you choose to draw the full actual rectangle or just draw a horizontal line is up to you. For this first video, for this first time, I will draw the rectangle so you can see it and you can think about it like that. Because physically, that is the whole idea behind the problem. Break up your larger area into lots of little rectangles that are parallel to the surface of the water. Why would you do it that way? Well, because the rectangle is parallel to the surface of the water, that means the fluid pressure acting on that thin horizontal strip is constant. So we can figure out the fluid pressure. We know the area of a rectangle, therefore we can find the fluid force. And if we know the fluid force on that small little rectangle, we can then use an integral to add up all of the fluid forces on all of the small little rectangles, which will then tell us the fluid force over the entire surface, whatever that surface may be. Okay, so we know that the thickness, or the height, is dy of this rectangle. We need to know the area, so that means we need to know the width. Well, the width is easy in this case because the width is constant. Doesn't matter where we strike or we consider our thin little horizontal strip, the widths are always the same, and that is 2 meters. So the area of our rectangle at a depth of y is 2 times the thickness, dy. Step 3 in this general procedure is to calculate the pressure is to calculate the fluid force. So we need to know the pressure and the area. So I just noticed in my general procedure, step 1 is not to calculate the depth, it's to calculate the pressure, which we need the depth. So let's just note that for a moment. But pressure is going to be our depth, y, times density, rho, acceleration due to gravity, g. That's our pressure. Okay, so the force then would be pressure times area. So this would be y rho g times 2 dy. And then step 4 is to integrate over the entire surface. So 2 rho and g are constants, so I'll pull them out. So we really just have y dy. And then we are integrating from, well, this y value, which is going to be positive 3 since we chose to direct our y-axis positive downward. We oriented it differently, that's fine. So it would go from this y value of 3 to this y value, which is 5 more than 3, so 8. So this would be the integral from 3 to 8 y dy. So this is rho g y squared, because the 2's would cancel, 3 to 8. So rho g times 64 minus 9, whatever that is in newtons. That'd be the total fluid force.